Dawood Alavi? Sam? Stephen Johnson? Thank you. Carson? Elena? Wei? Lee Hong? Here. Thank you. Kobe Davis? Alexander L. Mai? Nick Gilbert? Yogi? Grady Cook? Grady? Andrew Gonzalez? Cody Weinhold? Cody? Wang Chang-Su? Ming Liang? Janosh? Frank San? Jeffrey Berta? Puna Narani? Puna? Sanjay, please. Sanjay, thank you. Trisan A. Trisan. Passing around the attendance sheet if you need to sign it. Here. Oh, it's not here. Sorry. I click. Yes. Now we do it. All right, if you have to turn in homework here. All right, so we are getting to the end. We cover all the material, and we have this lecture and the next one to address anything you want. Review material, do exercises, expand, anything. Yes? All right, so I'll write here. I'll start writing here all the questions, so maybe we organize them a little. So, which problem is this? 8, number 10, and is about
The question was for a 4-node graph, how many different...
interesting. Isomorphism. Right, sometimes knowing the number different give you an idea of what you are doing better. I think we had the same for Boolean function. If you have a Boolean function of 2 arguments like AND, OR, exclusive OR, how many can you have? Because this gives you an idea what really is the function. So yes, we do it. Someone else has another question?
Number 7.
Number 7 of this one. All right. Any other things bigger than a homework problem? So I'll start with this. So problem homework 8, which is due today, right? So, if you haven't turned in the homework, give it to me now, because now I'm telling you the solution. It's fair enough, right? Is anyone finishing it? All right. So, let's see what is being asked here. Number 10. The number of different graphs with 4 nodes. So, every graph has 4 nodes as far as this question is concerned. If I have 2 graphs, how can they be different?
Different number of edges.
Okay, this is good. You are on track. Can you be more precise? And this is not the joke. You know the joke, right? Not the joke.
Different number of edges unless you know they connect.
Right, right. So here, I'm not talking about isomorphism, right? I'm talking just different. So when 2 are different, when one has an edge and the other one doesn't have that edge, they are different, right? Forget everything else. If between 2 nodes, one has an edge and the other one doesn't, they are different. Are you with me? So here I have 4 nodes, A, B, C, D, A, B, C, D, and suppose that here I have an edge, and in the other I don't. Then I don't know if there are other edges there. Maybe, maybe not. But these 2 are different. You with me? All right, so how many times one can have an edge and the other one cannot? So here, in how many ways one can have an edge and the other one cannot? It's the number of edges. For every edge, either you have it or you don't, right? All right, so if we count the number of edges, each graph can or cannot have that one. So this is a combinatorial problem, right? Yes?
But if you just have one edge, is the graph like with A and B connected, not isomorphic? The graph has A and B connected.
So they are isomorphic, but here I say non-isomorphic. I say different,
Isomorphic.
right? If you want to do it isomorphic, it becomes much more complicated. You probably were there already, right?
That's what I don't.
Yes. Oh, all right. So, I don't know if I gave this principle here, but every time you can make your life easy, in this class and in real life, do it because life is hard enough. All right. So, how many edges there are at most? 6. How do you compute this? Is a permutation? Is a combination? Are there repetition? Are there not repetitions? Say that again?
Combination with repetition.
Combination with repetitions of what? All right, so now we have to readjust it a little bit. So here we have a set of 4 vertices, right? A, B, C, and D, right? So when do you have an edge? When you pick a 2 and you disregard the order, right? And so this one is what? Combinations? No repetition. Well, we counted that or not? I wasn't thinking about that. But then maybe we can put it there. Yes? And then the number changes. All right. All right. So typically we in a graphs almost always so we don't. So I wasn't thinking about that. But now we can argue whether it was or not.
Okay.
So suppose that you don't have a cycle on a node to itself. So how many we have? AB, AC, AD, BC, BD, and CD, right? And so 6. So what do we have here? 2 to the 6, right? These are all the possible graphs of this kind. You with me? And so it would be 2 to the 6. If we allow edges from one node to itself, then we can have it or we don't. And so it becomes, instead of 2 to the 6, 2 to the 10. If we allow edges from one node to itself, then we have 4 more. And so it becomes 2 to the 10.
So don't you have to worry about,
I'm sorry?
you're talking about isomorph, don't you have to worry about the,
No. Here, I'm not talking about isomorphic. I'm talking about different.
okay.
So, because if we do isomorphic now, AD, if you have an edge AD, and in the other one you have an edge AB, these are isomorphic. And so now it becomes much more complicated. Right? It's not enough to count the number of edges. It's also where the edges are.
Yeah, that's the problem. So if you get 2 to 6, don't you have to start talking about like how you cut down the value based on your,
Right. I don't know how to do it. It's very complicated probably. Or I don't have any good idea.
that's what it is. So like you just have to go through and try them. Like, let's do
So
something.
here the question, the way I meant it, was an easy question. The way I meant it is number of different. Forget isomorphism.
Okay, that's what you're.
So what I meant by non-isomorphic means forget isomorphism. Just consider them different.
I thought when you said non-isomorphic.
Yeah. Now that I read it, I understand your interpretation. All right.
Okay. No, that's why I like.
So homework is good for reasoning about these things. So it's good that we go to this and this and this. All right. So why, if we consider isomorphism, is complicated? Because even if you counted the number of edges, here you have 3 edges, right? And here you have 3 edges. These 2 graphs are not isomorphic. So looking at the edges is not enough. All right, yes?
I'm just curious, is it always 2e squared?
I'm sorry.
Would it always be 2e squared, or is it just a coincidence of the problem? Or,
I think if we have the same 4 nodes, and we want to see how many are different, but yes, it will always be 2 to the. All right. Someone else asked a different problem, right? Which was 7. All right. So, should we do it? So, this is a problem of shortest path. Let me make this a little bit smaller. All right, so we start from node 1. I'll just draw this one. I don't need very much. Here I have 1. Let me copy this on paper because otherwise it's difficult to do. This is directed, so I have a 2, and I have a 3, and here I have cost 2, cost 4, then I have here a 1, and then I have a 4 to node 4, and I have a 3 to node 5, and I have a 2 from 2 to 5. I think this is enough, all right? So I start with 1. This has the shortest distance, so 1 goes in the tree, right? So now, because I have here a distance 0, I updated the distance of this, that this is infinity. Here I have infinity everywhere when I start. And so here what do I get? 0 plus 2. So I change this into 2, and I change this into 4. Yeah? And I say, look, to go to 2 I come from 1, and to go to 3 I come from 1. All right? So now which one do I put in the shortest path? 2. So I put here node 2. All right? And so now what I do, the one that and I put the 2 in the shortest path. Now the one that I can reach from 2, I update the distance if this can be smaller. So here I have a 4. Can I, if I go through 2, do I get something smaller? Yes. So this one becomes a 3. This one is infinity. So what do I bring it down to? 4. And this one is infinity. What do I bring down to? 6. So here I have a 3. Here I have a 4. And here I have a 6. So which is the one that is going to the 3? 3. And I mark it down. And so now I pick the one not picked yet with the shortest distance. Which is it? 5. And so I put the 5 here, and I computed the distance to all the other ones. And so the order in which you go in the tree are 1, 2, 3, 5. Yes? I forgot to ask this one. Did I answer the question? All right. Far so good? So I propose a problem, and maybe we have a little bit of fun in solving it. This is a problem of the meter, and I spoke with a student, and I couldn't convince him that the answer to this problem here, 27, is 5, 6. All right? So I thought, can we prove this empirically? Not a mathematical proof, but at the end you say, well, I understand the word, but I'm not convinced. But something that is more convinced. You have an idea?
If you draw like the 2 dice, the 2 faces,
Yeah?
as a matrix, and then you put in.
And so this was my argument. I want to do it in a different way. Yes?
One is always going to be bigger than the other unless they're the same.
Correct. This is part of the problem. Yes.
So
my idea was, well, try to throw 2 dice and count how many times you get the condition, divided by the number of times you throw the dice, and see a little bit if you get something of this kind. So if you do it to 6, you should expect more or less that 5 times you get that condition, right? Is it convincing? Well, you can be very lucky and you do 6 times and 6 times you get the condition, or very unlucky and you do 6 times and you never get it. So it's not so convincing. Well, try to do it 60 times. Now you should get close to 50, right? Try to do it 600 times. You cannot be unlucky 600 times and get all the same. It doesn't sound right. Or you can do it 6,000 times. So why don't we use a computer to do this instead? Should we? And see how it goes? You have a question. I can answer now or I can answer later. But so basically, I want to write a program that does a simulation of this. Yes, thank you. That does a simulation of this. And we'll see that the program is very versatile, because then we have another problem which is even more difficult than this, and we can do also that. So it's something general, this. So let me go to an empty directory, and I do my simulation in Ruby. So I have a constant k. This is the number of times I throw the dice. So I start with 6. Then I define a function that does the simulation. And now I have a counter of the event. And I start with 0. And now I do from 1 to k times. What do I do? Well, I need a random number generator, and turns out that Ruby has one, which is good. So I call this a pseudo random generator, and there is a class random new that gives to me. So now every time I call this pseudo random generator, the appropriate method will give me a simulation of throwing a dice. And I do it in this way. Dice 1 is the pseudo number random number generator dot I think is rand 1 6. And so this will give me a value between 1 and 6. All right? Now I want to throw 2 dice. So I have dice 2. And here I'm happy enough to print D1 and D2. Oh, sorry, thank you. This is called pair programming. Do people know about pair programming? It's a real thing. And so now if I do Ruby times why times is not defined? Times. All right, let me, I don't, let me clean some windows here. And I cannot get the network. Oh, you don't see, but it's trying to get the network. It didn't. Let's see if the second times we are luckier. No. Maybe it's do.
Yeah, it's dot times do. I think it's dot times and then space do. Not dot, just space.
I don't like it.
That's what static space is telling me.
All right. How would I do without you? So let me do it this way, which I think sorry, is uppercase K. Oops. All right. So we do it this way. All right. So this is my simulation. with a little bit of surprise. What is the surprise? I have 2, right? The number should say 1, so it's not as convincing as I wanted. This time also, you know, who knows how is the random number generator? All right, this time I had it only once, right? So let's do this. Instead of 60, let's do this 600 times. And I don't print it because then it's too long, I cannot even read. But here I say, count, add 1, if, and now I have the condition. And what is the condition? The condition is the top face of one is greater than the other. So here I will say D1 is greater than D2. I'm sorry? D1 is greater than D2, or D2 is greater than D1. Yes? Oh, and then after this loop, I print a count. So, print a count. Yeah? Oh, no, we'll get there, thank you. But yes. And so, 501 is incredibly precise, this one, right? It's really 5, 6 for that little oddity. Actually, I think if I do again, probably I won't get so precise. Well, 3. Yeah, 3 again. So, I find it very convincing. So now, if you want to normalize, regardless of the count, how do we massage count? So I should divide it by k, right? This is integer division because both are integers. And so what do I expect here? Which number do I expect? Say that again? Oh yes, lowercase, thank you, pair programming. So this will be a percentage on out of 1, right? So just to make my life easy, what happens if I multiply this by 6/5? Because this is 5/6. I bet something very close to 1, right? So if I multiply this one, I expect something close to 1. All right, 98% close. 101% close. This is very precise. This also. So what if I do 6,000 times? I get even closer, right? So let me print this better. How do I print this? With the 2 decimal? All right. So it looks like on 6,000, the difference really from the theoretical value is 1% or less. I hope it was convincing. So now here we had another problem that was conditional probability, which is a little bit more complicated. Is this one here. And if we do it, probably it helps understanding better this concept of conditional probability. So here says, what is the conditional probability? That the sum, they show the same face if the sum of the faces is less than 4. So how do I change my program to do this? So the conditional probability, here I have 2 events. What are the 2 events? One event is that they have the same face. The other one is that the sum of the faces is less than 4. So it says the conditional probability is the intersection of these two events divided by the probability of the second event, the one that I know. So here I start, so here I will put two counters. So I have a count event E and count event F. Event F is that the sum of the faces is less than 4, right? So here I will say count F, I increment by 1 if what? Oh yeah, sorry. I put two counters for the two events. F is the given one, the one that I know that occurred. So I increment it if the sum of the faces is less than 4. So D1 plus D2 less than 4. The other one is intersection. So for the intersection, I say this one and the faces are equal, right? So I change the program a little bit because it becomes better. If the faces is less than 4, what do I do? Count F, I increment, and now what do I do? If the faces are equal, I increment the other one. And this is the intersection. So, count E plus equal 1 if D1 equal D2. Yes? And so now what do? I print D1 and I print D2, maybe normalized. So I print the F and the E, and I print with a 2 decimal. And so here I print what? I divided. So count F divided by K, but I have to add something because otherwise that's an integer division, and this is going to be 0 always. Count. So I don't know exactly how to do this in Ruby, but if here I add 0 plus this one, all of a sudden this is a floating point number, and so I get what I want, and the other one will be count E. Say that again? Sorry, I didn't get it. So is what we expect this one? So I think that this is something that helps understanding the problem, because you have to code it, so there is no hand waving. In a sense, it's like multiple choice, where you cannot argue that you can use the program. I don't think you need to use the program. Let's do this analytically and see how this goes. And then we try to interpret those numbers and maybe print them a little better. So here I have my dice 1, and here I have my dice 2. And so here I have 1, 1. Here I have 1, 2, 1, 3, 1, 4, and so on. Here I have 2, 1, 2, 2, 2, 3. Here I have what? 3, 1, and so on. So, the event F, the given one, where is it?
It's the top three.
The top 3, the sum has to be less than 4. So the only 3 that the sum is less than 4 are these here. Let me circle them in red. These 3, right? And so what is the probability of this? This is event F. 3 out of 36. Yeah? How much is the 3 out of 36? Is 0. Oh, you don't see it. Sorry. Is 0.833. So, what is the intersection here? What is the intersection of the two events? It's only this one here. So it's 1 out of 36, right? And so 1 out of 36, what is it? Is 0.0277. And so if in my simulation, instead of using 2 decimal, I use 4, so I have a 6.4, I can see how close I get to those. Oh, sorry. So these are the numbers I get. With 6,000, what if I do 600,000? All right, much closer. Much closer. Here they are. These are the numbers that I expected. And I get exactly this one. And here is 3 out of 10,000. And so, yes?
But then wouldn't the answer be the 1 over 36 divided by 2 over 36?
Yes.
Oh.
That's the same as one.
All right. So I just wanted to show that you can play with these things, and if you code them, you have to be very precise. And then this will give you some idea whether what you are doing is right or not. But I don't think the goal is just to make sure that you do it right, as maybe Sam was thinking. Where is Sam? It's hiding there now. But this is just because it forces you to think what is the conditional probability, how you measure, and everything else. All right. Hope you had fun. What do we do next? We can do problem, we can review concepts, and then do some problem to see whether we understand those concepts. Jimena, you want to propose something? I think here a good choice for everyone is here. I think I understand it, but I'm not completely sure. So let's look at it one more time. Yes? Binary relations. Fantastic. All right. binary relations. What do we have? Almost every concept has some key points. What are these key points? So the definition, right? When we talk about something, we want a definition, and most of the time we want an operational definition. Definition has to be something that when we look at the situation with the definition, we can say yes, no. What else do we have typically with the definition? Notation. Because in writing the definition and in reasoning about this concept, we write it in a certain way. So we must be sure that we know this, right? What else? Concepts that are associated with them. Properties, we have a number of properties. These are properties specific of a binary relation. Someone wants to mention some? Say that again? Reflexive. And there is a symmetric, a transitive, anti-symmetric. We have all of them, and we may address them. What else? Which other concepts are associated to binary relations? Composition, very good. I wasn't thinking about that. Composition. What else? Well, yes, inverse. Yes, before going there, that's good. Before going there, we have what? Right, equivalence classes, which are really related to this one. So let me do this one. Partial order, like Belen said, or Belen, sorry. Partial order. Equivalence. And equivalence carries what? Equivalence classes. What else? I remember at least one more. I may miss something, but I remember at least one more. A recent one. Very recent one. Very good. Very good. So, how do we call this? Duality with graphs? What am I referring here? That if you have a binary relation, you have a graph, and if you have a graph, you have a binary relation. Well, now we move to graphs. So, yes, but so is this enough as a laundry list? Should we focus on something or go over all this? Right, the definition and notation. All right, so what is a binary relation? On a set A is a subset of the Cartesian product A cross A. Should we see an example? So, here we just saw an example of this. Here we have a set A, which is the value 1 to 6. We have the Cartesian product, which are all the pairs, where the first is between 1 and 6, and the second is between 1 and 6. A subset is the one in red, which is the element that the sum is less than 4. So this is an example of a binary relation. Maybe it's not particularly interesting, but a binary relation is a subset of the Cartesian product of a set A. Any subset you want. Yes?
Would 1, 1 then be an equivalence class?
No.
No.
To have an equivalence class, you need an equivalence relation, and this, I don't think is an equivalence relation.
Can we review that after?
Yes. All right. What are other interesting binary relations? The one that we have been playing with in this class for the purpose of understanding. Equal, right? Less than, or less than or equal to, or greater than, yeah? Divides or is a factor of something. We've been playing with this. These are examples. Should we look at some in some details? If I look at a divide over the natural numbers, what do? I have the Cartesian product 0, 1, 2, 3, 4, blah, 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 0, 1, 2, 3, 4, blah, blah, blah. And here I have all the pairs. I'm not going to write them. And so I say this one divides the other one. So I call this A and this B, and my relation is A divides B. Where do I put the cross that A divides B? One divides what? 0, 1, 2, 3, 4. This column is full, right? 2 divides what? Does 2 divide 0? Yes. 2, 2, 4, and so on. Here, I skip 1 and 1 I do. Yeah? What about 3? Does 3 divide 0? 1 and 2? So I skip 2, and I put another one, I skip 2, and I put another one, and so on. I'm sorry?
Does that make 0?
Well, we haven't talked about 0 yet.
Well, I was just going to say, doesn't that make it the identity of the operator? Is 0 the identity of the operator?
No, it's not.
The identity.
No, we're not.
So, the argument are numbered, but the result is a yes or no here.
Oh, okay.
So,
I was expecting an outcome.
so does a 0 divide a 0? Typically, you learn that you cannot divide by 0. Right? Here you have to be careful with the definition. If you go on Wikipedia, there is a long discussion whether you should put it or not. 0 is certainly a factor of 0. Right? Because there is a number that if you multiply this number by 0, you get a 0. So some people put a cross here and say that 0 divides 0. Whether you put the cross there or not, at some point becomes a convention. Do whatever is more convenient. Unless someone is forcing you to consider one or the other. Does a 0 divide 1? Why not? Well, we just divided 0 by 0, so I want a stronger argument. Yes?
No matter how many zeros you add up, you never need it for 1.
And you are close. So, to say that divides, we say A divides B if and only if exists a C such that A times C is equal B. If you have this C, then you say that A divides B. So if you have this definition, if A is 0 and B is 1, you can never find the C that you multiply. Except B is 0, because then every C is good. And so this is why I put this cross here. All right. And so we look at this one. This is maybe is an odd relation, divide. All right. So now what we look at, the properties. So let's look at one by one. Reflexive. When do we say that the relation is reflexive? And by the way, is this reflexive or not?
Yes.
Yes. So it's reflexive when for every x in my set, x is in the relation. If you want to look in this case, these are all the elements on the diagonal. You find all of them. So maybe it's good in this case to say that the 0 divides the 0. So we have a reflexive relation. It's nicer than a non-reflexive one. What does it mean that it's symmetric? If x is related to y, y is related to x. If x is not related to y, then you are fine. So is this symmetric? No. Who can tell me why not? Let's hear someone else.
When you have one is related to two not related to.
Fantastic. This is really the answer that I'm looking for. Just one example that shows that this is not true for every x and y. To show that it is not true for every x and y, you just show for one particular x and one particular y. Cannot be more convinced. So here we have that 1 divides 2, but 2 doesn't divide 1. And so it's not symmetric. Transitive. What does it mean that transitive? You pick a 3 element any way you want it there, x, y, and z. If x is related to y and y is related to z, then x has to be related to z. So first, let's see whether we spot a case where this is true or we spot a case where this is false. If it is false, if we spot a case where this is false, we say that it's not a transit. If we spot a case where this is true, well, we have to look for all the other cases or figure out that this is true not for that particular case, but for every case. So can you spot a case where this is false? I can. I just don't see it. Can you spot a case where this is true? Yes. Let me tell you one, simple enough. 1 is related to 2, and 2 is related to 4, and it turns out that 1 is related to 4. So this is encouraging. So 1 are related to 2 because 1 fits an even number of times in 2. Without a reminder. 2 is related to 4 for the same reason. So, but if 1 fits an even number of times, even in the sense that there are no reminders in y, then even better fits an integer number of times in z. And so yes, this is transitive. Is everyone on board, or should I explain a little bit more? Yes?
So this relation here is not symmetric.
It is not symmetric because we saw an case.
And so the binary relation is reflexive, transitive, and antisymmetric? Not.
We haven't gone there to anti-symmetric yet.
So far, a binary relation is
Yes.
reflexive and transitive.
This one, yes.
Not symmetric.
Not symmetric. We can see whether this is anti-symmetric, which is the last property. Do people remember what anti-symmetric means?
If X is related to Y and Y is related to X, it has to be the same.
Right. And so here, we have to say, suppose that A divides B and B divides A. Can they be different? All right, I'm thinking because of 0. If we take out the 0, certainly So does the 0, all right, so I think it is anti-symmetric. Clearly, if the number are not 0, neither is 0, this is certainly true, right? Why? Because if you cannot have the 1 divides 2 and 2 divides 1. If x divides y and y divides x, they have to be the same.
But if we don't have it the other way around, it doesn't matter, right?
Right, it doesn't matter.
So, like, all these numbers are factors of 0, but 0 is not a factor of anything but 0. So.
Except the 0, but they are equal, so we are fine. So is anti-symmetric. Kim, are you convinced or not? Good. All right.
So I think I didn't get that answer. When it's only one way, when it's the other way, then it's not.
Right. So let's write this here to make sure that first we are all on track. So anti-symmetric. This is for all x, y, and z in A. If x is related to y and y is related to x, then x is equal y. All right? This is the definition of anti-symmetry. So in this case, what does it mean x related to y? That x is a factor of y. What does it mean that y is related to x? Right. So what do we have? We have, if we want to be analytical, x times k is equal y. All right? And y times h, a different one, is equal to x. All right? So x times k times h is equal to y times h is equal to x. All right? So k times h has to be equal to 1. And these are integer numbers. So both are 1, and the consequence is that x is equal to x is equal to y, and y is equal to x.
So, but the fact of the 0, like you said, are we including that 0 divides 0?
Well, so now we have that 0 divides 0, and here we need this 0 divides something else, right? 0 divides 0. They are equal. So basically, in this formula here, replace this with 0, 0. Right? And so here you have 0, 0, and they are equal. Yeah? All right. Should we take a break?